Welcome to module 2 of chapter 8. In this module we are going to study adjacency matrix of a graph. The adjacency matrix is an n by n matrix where n is the number of vertices of the graph, which is a 0-1 matrix and is defined as the ijth entry of the adjacency matrix is 1 if I is adjacent to vertex j, otherwise 0. From now onwards, eigenvalues and characteristic polynomial of a graph, we mean that eigenvalues and characteristic polynomial of adjacency matrix. Now we are going to show that the ijth entry of a power k gives the number of walks of length k from vertex I to vertex j. Because of that, we can show that the trace of a square is equal to the twice of the number of edges in the graph, and trace of a cube provides information about the number of triangles in the graph. In module 2 of chapter 8, we are going to study adjacency matrix of a graph. The learning objectives of this module are introduction to adjacency matrix of a graph, adjacency algebra of a graph, co-spectral graphs, distance matrices of a graph. Introduction to matrices of graphs. There are various matrices associated to graphs. So, given a graph, we can associate several matrices which record information about vertices and how they are interconnected. The question then arises, given that you know the eigenvalues of some matrix associated with the graph, what can you say about the graph? Spectral graph theory looks at answering questions of this type. By looking at these eigenvalues, it is possible to get information about a graph that might otherwise be difficult to obtain. Adjacency matrix of a graph. Let X be a graph on n vertices. Let us fix a labeling of the vertices of X. Then the adjacency matrix of X denoted A of X, which is equal to Aij, or simply we can say A. If X is clear from the context, instead of writing A of X, we simply say A, is an n by n matrix with Aij is equal to 1 if ith vertex is adjacent to jth vertex and 0 otherwise. Note that another labeling of the vertices of X gives rise to another matrix B, such that B equal to P inverse into AP for some permutation matrix P. For a permutation matrix, recall that we have P transpose is equal to P inverse. Hence, we talk of adjacency matrix of a graph X and we do not worry about the labeling of the vertices of X. So, if you change the labeling, we will get another matrix that is similar to the original matrix A. So, their eigenvalues are going to be same. Clearly, the adjacency matrix A is real symmetric matrix. That means, actually we are considering adjacency matrix of a simple graph. It is undirected and as well as finite. So, A is a n by n matrix. Hence, A has n real eigenvalues and A is diagonalizable, and the eigenvectors can be chosen to form an orthogonal basis of R power n. The eigenvalues, eigenvectors, the minimal polynomial and characteristic polynomial of a graph X are defined to be that of its adjacency matrix. So, now onwards we say eigenvalues of a graph means that eigenvalues of its adjacency matrix. Minimal polynomial of a graph means minimal polynomial of its adjacency matrix, and so on. If A is adjacency matrix of a graph X, then we denote FA. In general, C of A, C is the complex numbers, or you can take any field in fact, but generally we will confine to complex numbers. F of A is a subalgebra of Mn of F generated by A. That is actually F of A is set of all polynomials in A with coefficients from F. As we already pointed out, we will take coefficients from complex numbers. It is denoted by A of X. called adjacency algebra of X. So, adjacency algebra of X is a set of all polynomials in A, and you can show that it is an algebra. Algebra, what we mean is it has both vector space structure as well as ring structure. We will illustrate with till now what we done, we will illustrate with an example. Let us take graph is K3, then its adjacency matrix is 0 1 1 1 0 1 and 1 1 0. It is because 1 to 1 there is no self loop, so there is no edge from 1 to 1, so 0, but there is an edge from 1 to 2, there is an edge from 1 to 3. So, entire row of first row is contains ones except the diagonal element. So, the adjacency matrix of a complete graph, only diagonal elements are 0, remaining all are going to be 1. The characteristic polynomial is x minus 1 whole square into x minus 2. The minimal polynomial of A or x is x minus 1 into x minus 2, and the adjacency algebra in this case is alpha I plus beta into A, where alpha beta belongs to complex numbers. Now, we are going to prove that number of walks of length k from vertex I to vertex j is obtained from in the a power k, ijth entry of a power k. So, the statement is, let x be a graph with a adjacency matrix A, then for every positive integer k, a power k ijth entry of a power k is equals to the number of walks of length k from vertex Vi to vertex Vj. So, the proof, we will prove the result by induction on k. Base step, if k equal to 1, by definition Aij is equal to 1 if Vi and Vj are adjacent, 0 otherwise. This is the definition of adjacency matrix. Assume the result is true for k equal to L. Now, consider the matrix A power L plus 1. So, the ijth entry of A power L plus 1 is equal to summation h equal to 1 to n A power L I h into A I h j. So, therefore, ijth entry of A power L plus 1 is equal to number of walks of length L from Vi to Vh, then a walk of length 1, that is adjacency, from Vh to Vj for all vertices Vh of V, that means vertex set of X. Thus, A power L plus 1 ijth entry equals to number of walks of length L plus 1 from Vi to Vj. As a corollary to this result, it is easy to see. So, we are omitting the proof. Let X be a connected simple graph on n vertices. Capital gamma ij of k denote the number of paths of length k from ith vertex to jth vertex. Also, n be the matrix whose ijth entry is given by nij is equal to summation k equal to 1 to infinity gamma ij of k into x power k. That means it is a power series, each ijth entry is a power series. Then n is equal to 1 by identity matrix minus x times matrix A, the adjacency matrix. Now, we are looking important result, what the trace of the adjacency matrix will provide to us. Let A be the adjacency matrix of a simple graph X, which is equal to V comma E. Let lambda 1, lambda 2 and so on lambda n be the eigenvalues of A. Then lambda 1 plus lambda 2 and so on plus lambda n is equal to 0. That is, sum of the eigenvalues is the trace. So, trace is equal to 0, and lambda 1 square plus lambda 2 square and so on plus lambda n square is equal to twice the number of edges. As we know that modulus of E of x is the number of edges in the graph. So, it is important that trace of A square is giving the twice the number of edges. So, if you can understand that by using adjacency matrix, it is possible to find the number of edges, and lambda 1 cube plus lambda 2 cube and so on lambda n cube is equal to 6 times t of x, where t of x is the number of triangles in the graph. So, now that means the trace of a cube is equal to 6 times the number of triangles. Now, we are look at the proof of this one. Let A be an n by n matrix with eigenvalues lambda I of A, where 1 less than or equal to I less than or equal to n. Then lambda 1 plus lambda 2 plus and so on lambda n is equal to trace of A, that we know earlier from the results of matrix theory. Lambda 1 square plus lambda 2 square and so on lambda n square is equal to trace of A square. Lambda 1 cube and so on lambda n cube is equal to trace of A cube. But lambda 1 plus lambda 2 plus lambda n is equal to 0. As x is simple graph, its adjacency matrix A has zeros on the diagonal, hence trace of A equal to 0 or sum of the eigenvalues is equal to 0. So, use equation 1 to get the required result. Now, lambda 1 square plus lambda 2 square and so on lambda n square equal to twice the number of edges. Note that we have to show. Note that diagonal entries of A square counts the number of closed walks of length 2, that is A square of I is equal to degree of Vi, the ith vertex of x, that is trace of A square is equal to summation I is equal to 1 to n degree of Vi, but we know that sum of the degrees of all vertices is equal to twice the number of edges. Thus, the result follows using equation 2. Now, we need to show that lambda 1 cube plus lambda 2 cube and so on lambda n cube is equal to 6 times number of triangles. Note that the diagonal entries of A cube counts the number of closed walks of length 3. Hence, trace of A cube is equal to summation I is equal to 1 to n A cube II, that is equal to 6 times number of triangles of x, as each triangle say formed by the vertices I j k are counted as a closed walks of the form I to j from j to k and k to I, I to k to k to j and j to I, j to I to k to j. Like that, we have for a single triangle we are counting 6 times, starting with I 2 times, starting with j 2 times, starting with k 2 times. Thus, the result of follows. Hence, the proof that the spectrum simple graph x determines the number of vertices, edges and triangles. Now, we will going to see co-spectral graphs. What is a co-spectral graph? Two graphs are said to be co-spectral if they have same eigenvalues with same multiplicities. For example, if you look at this graph, these two graphs, it is clear that isomorphic graphs are co-spectral, but the converse need not be true. In the figure shown above, that two graphs, one is K1 union C4, that is a cycle and we put one vertex in the middle. So, that is K1 union C4, and K14 star graph with 5 vertices are co-spectral, as both have the same characteristic polynomial x cube minus 4x cube, but they do not have same number of 4 cycles. Thus, we see that several properties of graphs cannot be determined by graph spectrum, that is connectivity, degree sequence, etc. The following graphs are the smallest co-spectral connected graphs which are not isomorphic. This graph as well as this graph, we can show that they are not isomorphic, but they are co-spectral. That means they have same adjacency spectrum. That means eigenvalues of the adjacency matrix of first graph and the eigenvalues of adjacency matrix of second graph are equal. Now, we will count the total number of walks of length k. Next, suppose that we want to count total number of walks of length k in a simple graph x on n vertices. Then we need to consider E transpose A power k into E, where A is the adjacency matrix of x and E is a column vector of all ones. As A is a real symmetric matrix, its eigenvectors say x1, x2 and so on xn corresponding to the eigenvalues lambda 1, lambda 2 and so on lambda n can be chosen from orthogonal basis of r power n. Then for some appropriate constants ai's, Ei is equal to I is equal to 1 to n ai xi, where again recall capital E that E is bold E is column vector with all ones. Thus, one can check easily that E transpose A power k into E is going to be summation I is equal to 1 to n a xi transpose into A power k summation I is equal to 1 to n a xi. So, if you multiply A power k, if you take A power k inside the second summation and the fact that each xi is an eigenvector of A, so it is automatically eigenvector of A power k. So, we have summation I is equal to 1 to n a xi transpose into summation I is equal to 1 to n ai lambda I power k into xi, which is equal to summation I is equal to 1 to n ai square lambda I power k into xi transpose into xi, which is equal to I is equal to 1 to n ai square lambda power k. We proved that isomorphic graphs have same eigenvalues. That means, if x1 and x2 are two isomorphic graphs, the eigenvalues of x1 are equal to the eigenvalues of x2. But converse of this result is not true. That means, there exist graphs, their eigenvalues are same, but they are not going to be isomorphic. We named them as co-spectral graphs. Now, we are going to prove following thing. We are going to assume that if D is a diameter of the graph x, then we are going to show that the adjacency matrix of the graph x has at least d plus 1 eigenvalues. And also we are going to show that the dimension of adjacency algebra of the graph x is equal to the number of distinct eigenvalues of x. So, consequently, if d is the diameter of the graph x, then the dimension of adjacency algebra lies in between d plus 1 and n, including d plus 1 and n. Now, we are going to show that the dimension of adjacency algebra lies in between d plus 1 and n, including d plus 1 and n. So, lemma says that let x be a connected simple graph on n vertices. If d is the diameter of the graph x, then d plus 1 is less than or equal to dimension of a of x is less than or equal to n. Since d is the diameter of x, there exists x comma y belongs to V with distance of x comma y is equal to d. Suppose x equal to w naught comma w1 and so on, x equal to w naught comma w1 and so on wd equal to y is a path of length d in x. Then from the lemma, previous lemma, we saw that for each I belongs to 1 to d, there exists at least one path of length I from w naught to wi, but no shorter walk. Consequently, a power I has a non-zero entry in a position where corresponding entries I, a square and so on, a power I minus 1 are 0. So, I, a square and so on, a power I minus 1 comma a power I is a linearly independent set. Thus, I, a square and so on, a power d minus 1 comma a power d is a linearly independent set. Hence, d plus 1 is less than or equal to dimension of a of x. Further, the upper bound is achieved by well known Cayley-Hamilton theorem. Hence, the result follows. As we know that by Cayley-Hamilton theorem, the maximum number of eigenvalues is n only. So, we have the result. Now, we will prove that the adjacency matrix has at least d plus 1 eigenvalues, distinct eigenvalues whenever d is the diameter of the graph. The above result has a nice consequence. In particular, it relates to the number of distinct eigenvalues of a simple connected graph with the diameter of the graph that we stated here as a corollary. Let a connected simple graph x with diameter d has at least d plus 1 distinct eigenvalues. So, it is a, though it is a direct consequence of the previous result, but this is a very powerful result that diameter d and distinct eigenvalues, these are related. So, a graph with diameter d, connected graph with diameter d has at least d plus 1 distinct eigenvalues. We will use this corollary several times. Since the adjacency matrix is a real symmetric matrix, its minimal polynomial is the product of distinct linear polynomials. Hence, dimension of A of x also equal to the number of distinct eigenvalues of A. Thus, if graph x has a diameter d, then it has at least d plus 1 distinct eigenvalues. So, though proof is not required, but we given the proof. The above corollary is not true for directed graphs. For example, the following directed path has diameter 2, whereas its adjacency matrix has only 0 as its eigenvalue. So, the directed path graph, there is an edge from 1 to 2, but there is no edge from 2 to 1. So, it is a directed path and its adjacency matrix is given as 0 1 0 0 0 1 and 0 0 0. Here there is we are going to put 1 in the entry 1 comma 2, since there is an edge from 1 to 2. There is no edge from 1 to 3, so it is 0, and also we are not taking entry from 3 to 2 as we are not taking entry in the 3 to 2 as 1. It is because there is no edge from 3 to 2, but there is an edge from 2 to 3, directed edge. So, the path graph and n vertices has n distinct eigenvalues. This is one of the nice application of the previous corollary. As we already mentioned, we are going to use that corollary several times. So, since a path graph on n vertices, the diameter is going to be exactly equal to n minus 1. So, diameter d plus 1 eigenvalues, a graph will have at least distinct eigenvalues. So, the diameter of path is n minus 1. So, path graph has at least n distinct eigenvalues. If all eigenvalues of a simple graph are equal, then its diameter is 0. Thus, simple graph has only one distinct eigenvalue if and only if it is a null graph. Let x be a connected graph, then it has exactly two distinct eigenvalues if and only if it is a complete graph. That is, diameter of the complete graph is 1. So, it is a very nice result that it has two distinct eigenvalues if and only if it is complete graph. So, by using eigenvalues we are characterizing the graph. Let x be a graph with two distinct eigenvalues and then x is a regular graph. That is also a nice property. That means, if you have a graph has two distinct eigenvalues, we are saying that x is a regular graph. The proof goes like this: let x be a graph with two distinct eigenvalues, then dimension of A of x equal to 2, hence I and A forms a basis for adjacency algebra of x. Consequently, A square is equal to small a into capital I identity matrix plus b into A, where A and B are some integers. Thus, A square of ii is equal to A for all I. That means, every diagonal element entry of A square is same, that is equal to A. So, that is why it is a regular graph. As we know that the diagonal entry of A square gives the degree of the vertex. Now, another result is, let x be a connected graph on n vertices. If A is its adjacency matrix, then every entry of I plus A whole power n minus 1 is positive. This result we are going to use in other modules also. So, there we are not going to give proof. So, reader has to recall this proof whenever required. So, this is an important result. From lemma 1 we see that ijth entry of I plus a square and so on a power n minus 1 equal to total number of walks of length less than or equal to n minus 1. As in that lemma we proved that the ijth entry of a power k gives number of walks of length k from I to j, but now we are adding a square, a cube and so on a power n minus 1 including I. So, it gives total number of walks of length less than or equal to n minus 1. As x is connected graph on n vertices, diameter of x is less than or equal to n minus 1, hence each entry of I plus a square and so on a power n minus 1 is positive. Thus, the result follows from the fact that I plus a whole power n minus 1 is greater than or equal to I plus a square and so on a power n minus 1. Here one has to define what is here greater than or equal to. How we are defining greater than or equal to among the matrices? It is simply if I take ijth entry in I plus a whole power n minus 1, that has to be greater than or equal to ijth entry of I plus a square and so on a power n minus 1. That means, we say that two matrices A and B, and we say that A is greater than or equal to B if every ijth entry, every entry in A is greater than or equal to every entry of B, ijth entry of B. Now, we are going to define kth distance matrix of a graph. Let x equal to v comma e be a connected graph with diameter d. For 0 is less than or equal to k less than or equal to d, the kth distance matrix of x is denoted ak, is defined as ak rsth entry is equal to 1 if the distance from Vr to Vs is equal to k, 0 otherwise. So, now we are going to define d plus 1 matrices like this. The first matrix is A0, that is identity matrix itself. A1 is the adjacency matrix. A2 onwards we will get other matrices. All are 0 1 matrices, and also we can see nice properties of these matrices. From above definition it is clear that A0 is identity matrix, A1 is the adjacency matrix of the graph x, A0 plus A1 plus AD equal to J. Remember that this J is matrix of all ones, that means every entry in J is equal to 1. AK for 0 less than or equal to k less than or equal to d is a symmetric matrix. Since we are looking the distance matrix of a graph, the adjacency matrix itself is symmetric. So, all these matrices are going to be symmetric. Thus, the set A0, A1 and so on a power d is a linear independent set in Mn of R. Now, we are going to define a graph by using the distance matrices. Let x be a connected graph with a diameter d. Let ak of x for 0 less than or equal to k less than or equal to d be the kth distance matrix of x. Then x is said to be distance polynomial graph if ak of x belongs to a of x, adjacency algebra of x. In other words, every distance matrix is a polynomial in the adjacency matrix of A. The complete graph Kn, the cyclic graph Cn, complete bipartite graph Knn, Peterson graph are few examples of distance polynomial graph. We request reader to verify these things, means why all these graphs are going to be distance polynomial graphs. If d is the diameter of the graph x, we denoted kth distance matrix AK, where 0 is less than or equal to k less than or equal to d, is the kth distance matrix AK is defined as the ijth entry of AK is 1 if there is a path of length k from I to j, 0 otherwise. We defined distance polynomial graphs as the graph in which all distance matrices are belongs to adjacency algebra of the graph x. That is, every distance matrix is a polynomial in the adjacency matrix of that graph x. With this, we end this module.